Hello. So people started showing up. I didn't think I was going to record this, but I've started recording it because more people started showing up to tutorials. So a few questions that people had about the class before now. Uh, some people were having questions about the AP study sessions. As long as you went to the first AP study session, your AP test will be covered. If you did not go to the first AP study session, you need to do 4 hours worth of material. So you can either do 4 hours of my dedicated review, which I'll set the hours later, or if you do 4 hours of the NIMSY sessions, you need to take screenshots of the NIMSY session, take at least a page of notes, and do all of the work during the session, and you can turn that in each of those for 1 hour. Uh, Another thing, your test is going to be tomorrow morning until Wednesday at night, so you have 2 days to finish it. I will log in at 10 a.m. and go through a few of the confusing parts about the test. So some questions we've had. We wanted to see graphing for a spring, so I decided to set up a question where mass m is pulled a distance d from equilibrium and released on a horizontal frictionless surface. So we look at time t equals 0. We pull back to a position d, released from rest, so no kinetic energy, maximum spring potential energy. Then we go through equilibrium really fast with a lot of kinetic energy, no spring energy. Then we go all the way to our negative amplitude where we stop before turning around, so no kinetic energy, all potential energy. And then we kind of go back through equilibrium back to our point here. So when we graph this, where do we complete one full period at? So at what position have we completed a full period? So equilibrium we haven't got. So to complete a full period, I have to go start and then return back to where I started. So if I start here, positive d, and then I go through equilibrium, then I go to negative d, I have to wait till I return back to my initial position. So if I started at time t equals 0 here, I've completed one period here, which means I've only gone through half a period by the time I get to my negative distance. So this is 1/2 of a period. So the equilibrium, when I first go through that, that's only going to be 1/4 of a period. So this will be 3/4 of a period. So I have a few ways I could graph this. Let's start with, say, spring potential energy versus time. And we can do kinetic energy versus time. Now, kinetic energy, 1/2 spring constant distance squared, that's always going to be positive. Our potential energy is going to be positive. Kinetic energy is always going to be positive, 1/2 mass times speed squared. So I could look here. So this is versus time. So let's look at my kind of significant points in time. So I could have at time t equals 0. I could have at 1/4 of the period, 1/2 of the period, and 3/4 of the period, and then one full period. So we'll see I start with a lot of spring potential energy. When I go through equilibrium, I have no spring potential energy. I end up with a lot of spring potential energy when I reach the maximum displacement. And again, because position is squared, the spring potential energy is squared. And then I go through equilibrium again on the way back, and I have no energy. And then I reach my initial position again, where I have a lot of spring potential energy. We're going to see some sort of sinusoidal wave. This is a cosine. And this is just going to keep repeating itself over and over again. As time goes on, assuming no energy loss will repeat, and these should all be the same. I just suck at drawing. This shouldn't be all the way over like that. And then I could look at kinetic energy versus time. So kinetic energy versus time, I start with no kinetic energy when we're released from rest. So this is at time 0, 1/4 of a period, 1/2 of a period, 3/4 of a period and 1 full period. So I start with no kinetic energy. Then when I go through equilibrium, I have a lot of kinetic energy. Then I get to my max amplitude, 0 energy, go through equilibrium, lots of energy, and then I have 0 energy when I return back to where I started. Again, this is going to be some sort of sinusoidal wave, kinetic energy always positive. And as time goes on, as long as I have no friction, my wave is just going to keep repeating itself continuously. But I could also look at energy versus position, right? So I could look at spring potential energy versus position on the graph. So here I only go between position negative amplitude, equilibrium, and my positive amplitude, so positive distance. On a vertical spring, yeah, so yeah, I could look at that. Give me a second. I don't think they're going to do that to you though, so that's why I've kind of shied away from that. So we have kinetic energy versus position. So looking at versus position, time just keeps on going forward, right? But our position, we're oscillating back and forth around that position. So I'd be at negative amplitude at our equilibrium position at 0, and then at our positive amplitude, our maximum position. So when we're at our far points, at our amplitudes, we have a lot of spring potential energy. When we're at equilibrium, we have no spring potential energy. And then the thing that keeps us from doing some sort of like cosine wave like we've seen before is just the fact that spring potential energy is 1/2 spring constant times distance from equilibrium squared. So that position squared is a quadratic relationship. And then kinetic energy at our endpoints, we stop. We have a maximum kinetic energy in the middle. Now, our total mechanical energy has to stay constant. So if I lose spring energy fast, I gain kinetic energy fast at my endpoints. And then here I'm losing energy slowly. So kind of like this. So we have an upside down parabola to keep our total mechanical energy constant. All right, so questions on those? And then I could either ask you to graph these, or I could ask you to explain anything that's happening at any point. So you're probably not going to have to do every single bit of this, but you could be asked to do individual parts of that. So I don't think I'm going to do this on a vertical spring with the gravitational potential energy, because all it's going to do is make the graph look skewed. So normally what I'm going to say is if they give you a vertical spring, they're going to be doing a little trick. They're going to be doing the trick that I've kind of talked about, how when I have a mass on a vertical spring, they just call this the new equilibrium position, and they pretend that spring is at equilibrium. So this is the system equilibrium, but they're just going to pretend that this is the spring equilibrium. And when they pretend that's the spring equilibrium, they're pretty much saying that the gravitational potential energy is canceled out by the spring energy, and they're usually saying to just ignore it. So yeah, even if they had something like this and they were asking you for spring energy, they would still be expecting these two graphs. Otherwise, I'll try to draw that for you. I don't think they're going to ask that, but yeah, otherwise it would get really messy because you would have a point. Let's do the same thing. So 0 seconds, 1/4 period, 1/2 period, 3/4 of a period, and a full period. So we'll start the same here. We go up to a height d, so we pull the mass up and then drop it, and it goes up and down. So this would be as it goes through the, yeah, it wouldn't even be spring equilibrium there. Yeah, so this would be the as it goes through system equilibrium. And then this one would be when it goes to the very bottom position, and then it passes back through the system equilibrium, and then it goes back through to this position here. Yeah, this really, yeah, it's never going to, this is where it gets kind of tricky defining things. So if it's stretched, it depends a lot on the spring. Yeah, is the spring here, and then when I put the mass, it goes down? Is it going through the spring equilibrium position or not? Or does it stay below the spring equilibrium position? So let's say we stay below the spring equilibrium at all times. Yeah, they're really not going to ask a question like this. So yeah, so you'd have to talk about, we never go through spring equilibrium, so that spring equilibrium position would be greater than positive d. And so, yeah, you're going to end up with, I'm just going to do this versus position, not time. That's just going to be too much of a mess. Spring potential energy versus position. We go negative d, and then we go to positive d, and then we have our equilibrium. We have our kinetic energy, negative position, equilibrium, positive d, position x. Kinetic energy is going to be the easy one. We're still going to stop at our endpoints and go fastest through the middle. So kinetic energy is going to look identical no matter what. It's our two energies that are going to be, or potential energies that are going to be kind of messy. So positive d, 0. So this would be gravitational potential energy versus position. Now our gravitational potential energy is just mgh. We're probably just going to put our 0 right here. So it'd be a paper mess up. It would just be a line like this. So yeah, we would have a linear kinetic energy. Yeah, at the lowest point. Yeah, so it would look like that, and then we would have spring potential energy would be, yeah, when we get to negative position, you're going to have a whole heck of a lot of spring potential energy. We're still going to have spring potential energy. This is our system equilibrium here. So yeah, we're going to have, yeah, I guess that's what it's going to look like. So here we're not at equilibrium yet. So we still have spring potential energy here. And it's just going to be kind of like a shifted over. No, we're not at a 0 there. It should still be decreasing. Yeah, they're definitely not asking you a question. I definitely am not asking you a question like this. And College Board is definitely not going to put a question like this on your AP test. Because it's not at a minimum here. We're not at the bottom of the parabola. It should keep going past that towards 0. And then when we add these together, it should shift this and make it a parabola. Yeah, you're definitely not getting a question like that. Should the spring energy for a system? So it's getting shifted. Oh, it's getting shifted. So you would have, it would be like a x squared minus x relationship. it might not look exactly like this, but I'm pretty sure it's going to look kind of like this because you're subtracting this linear part away from the parabola, and you never quite reach the zero. Probably something like that. Yeah. Because this is going to be your closest to zero spring energy, and this is going to be the most spring energy. So, yeah, your parabola would continue outside here and go up like that. So it's kind of like we're looking at a parabola here, but we're only looking, say, from like here to here on the parabola, and we're ignoring the rest of the parabola. So that's what our spring potential energy is going to look like. So this would be at negative distance when we're furthest away, and this would be at positive distance. This would be our spring equilibrium. And this would be somewhere in here would be our system equilibrium. So yeah, that's all I'm going to talk about. That's way more of a mess than anything you're ever going to see. So hopefully you're happy with that. How would you draw free body diagram when it's at positive position D? All right, yeah, that's a good question. So yeah, we're back to this vertical spring here. So at positive distance D, we're at our maximum height. So we're all the way up. If I lift the spring up and I drop it down, it's going to fall because I have a bigger force of gravity down than spring force holding it up. Then we're going to reach that again when the block is in equilibrium, not when the spring is in equilibrium. So block equilibrium, or we could call this the system equilibrium. Now, on the AP test, they're probably just going to say equilibrium. It's just me who's really deliberate about what equilibrium I'm talking about. Is the spring in equilibrium or system in equilibrium? They might just say words like the block is in equilibrium or something like that. But yeah, so we'll reach that equilibrium position for the block where our spring force up exactly equals our weight down. And then we go down past this point. So we get to a position of negative D. Once we get to this point, the spring has stretched a whole lot. So the spring is pulling up with a lot of force back, trying to slow us down and stop us and slingshot us back in the upward direction. So we end up with a really big spring force up compared to our weight down. And if I was drawing these all carefully, these weights should all be identical lengths because the weight of that mass is not changing. So that's a good thing to know, how to draw those, or say speed up, slow down, things like that. Any other questions on these springs before I look at that quiz from before the break? Wait, which quiz did I give exactly before the break? I forgot. Yeah, at the system equilibrium, our weight is equal to the spring force. Yeah, spring quiz. It wasn't this one, right? We already talked about this one, I think. Kinda. Is that the one we did? I couldn't remember if it was that one because we had a second one that I was going to give after the break. It's been weeks since then, and I just completely forgot. So we never went over it. All right, we can look at this one. I'm kind of too lazy to write everything out, so is it okay if I just talk about it? Not that I'm really giving you a chance. That's what we're going to do. All right, so this is almost identical to an old AP test question. So we had a block. We pull it. It's initially at rest right here. So if it's at rest with an uncompressed spring, what does that wording mean? So let's look at this. So in contact, we have an uncompressed spring. What is that trying to tell us? All right, so we're at equilibrium. And for this one, on a horizontal surface without friction, this is spring and system equilibrium. So the block is in equilibrium, and because there's no friction right here, the spring itself is in equilibrium. So we start off with at equilibrium, negative mass. The block is pushed back along the frictionless surface from 0 to negative d. So we pull it back to there. So now from here to here, we have a displacement from equilibrium is equal to negative d. All right, the block is then released, and then it reaches here. At position x equals 0, the block enters the rough part of the track, leaves the spring, and eventually comes to rest at positive d. So it launches, hits here, and then leaves the spring and continues going along here. Yeah, the coefficient of kinetic friction between the block and the rough track is mu. So here we're trying to graph our quantities. So again, we want to graph the quantities kind of one at a time. So let's just kind of look at these individually. So we have position, we have our energy, and we're doing kinetic energy and potential energy. So which energy is probably going to be easier to start with? Kinetic or spring potential energy? Kinetic? Yeah, we could do kinetic. That'll work just fine. All right, so kinetic energy, I release it from position negative d. So at position negative d, we release from rest. So I have kinetic energy here. Again, be sure to label. Then I go through equilibrium. And again, if it's no friction or spring and system equilibrium are the same. So at equilibrium, what can I say about my kinetic energy? Do we have to put exact values? No. So here it says sketch. You do not have to calculate the values on the vertical axis. Most of these words are plagiarized from the AP test. So most of the wording is almost identical to what they said. So no, you don't have to graph the vertical position. But you do have to be careful that if one is going to be the same as the other, then it has to be there. So we end up with a lot of kinetic energy at equilibrium. But then we hit the friction surface and we slow down and stop at position positive d. Positive d. Now, the shape here is really hard to get just by itself, so I'm going to ignore the shape for now. So let's look at spring potential energy. I pull back here. So I start with a lot of spring energy, positive or negative spring energy. Yeah, right. Spring energy, spring potential energy, 1/2 spring constant, always positive, times that displacement from equilibrium squared. So I square a number, that's always going to be positive. We're not dealing with imaginary positions or anything. So I start with a large positive spring potential energy. And then you do have to make sure these are at the same height. I go through equilibrium, and then my spring ends up without any potential energy there. And we leave the spring. So let's make sure we actually shade in that spring potential energy here. But now, what shape do I have here? 1/2 spring constant times position squared. That spring isn't changing, so this is all constant. Energy versus position. But that position, that distance value is squared positive. So I have a positive parabola. Like this. All right, so I have that. And then because my total mechanical energy has to stay constant here, no friction, so that means spring potential energy plus kinetic energy has to stay constant. So if I lose spring energy fast, I gain kinetic energy fast. Here I'm losing spring energy more slowly, so I'm gaining kinetic energy more slowly. So my graph should look kind of reverses of each other. this. So points you could have gotten. 1 point for kinetic or total mechanical energy staying constant. Another point for the correct shapes, the correct curved shapes. 1 point for drawing the spring potential energy is 0 right here. That was a point given on the AP test. So real easy point. If you just sat there and drew both lines on the x-axis, you got 1 out of 4 points if you labeled everything. Now, this last bit, getting the kinetic energy to go down like this, is one of the more difficult things to see. But that last part there just has to deal with the fact that we have our, I could do work is equal to force times distance. So I could say my change in kinetic energy, right? Because I only have kinetic energy here, no spring potential energy there. Change in kinetic energy is going to be force of friction times distance, or force of friction, coefficient of friction, mass times acceleration due to gravity times distance. Well, coefficient of friction, mass, acceleration due to gravity is constant. So kinetic energy, well, and it's negative, I'm losing energy. So kinetic energy is proportional to position to the first power, which means linear, right? So a lot of little concepts in there. And we talked about this one right before the quiz, I think. All right. So then we have this part. So the spring is now compressed half as much to negative 1/2 d. The students asked to predict that the final position of the block will be half as far as, so instead of going to d, it goes to 1/2 d. The student reasons that since the spring will be compressed half as much, the spring will have less energy when it leaves the spring. So it'll slide a shorter distance along the track before stopping at position x equals 1/2 d. So what are they correct about? And why? I know obviously you can just see my answers right here. But where are they correct? I mean, they didn't compress it as far. So if they didn't compress it as far, I know spring potential energy is 1/2 spring constant times that distance from equilibrium squared. So if they didn't compress it as far, there's less energy. If there's less energy when the mass leaves the spring, it will slide a shorter distance, right? That's all correct. So not compress as far, less energy, and then it won't go as far. Now, this next part B, anytime it says what aspects are incorrect, a lot of people immediately go to correct it and then write it in a corrected form. But when it asks what's incorrect, just say the thing that's incorrect. So the thing that's incorrect, it would be saying the fact that it has half compression, so it has half as much energy. So that'd be the first thing to say. The student says the thing has half as much energy, which means it'll go half as far. So those are the things to see. Well, obviously we don't have half the energy because it's distance squared. So if I square 1/2, I end up with 1/4. So if I go half as far, 1/2 squared is 1/4. I only have 1/4 as much energy. So I'm only going to go 1/4 as far. And then that's where we can go through all this math, actually figuring out how far it goes. So we know, so this is C. So I know work is happening, right? Work is change in energy is force times distance times cosine of the angle. Well, work, looking between from equilibrium until it stops, equilibrium, to rest. So we're talking about change in kinetic energy specifically. At equilibrium, it's going really fast. We've left the spring, so no spring energy, and then I slide and stop. So we're talking about change in kinetic energy. Now, I don't really care about the cosine theta. That's just saying my velocity is to the right, but my friction is to the left. When I do cosine of 180 degrees, I get a negative. So all that's saying is I'm doing negative work. My friction and direction of motion are in opposite directions. I do negative work. Force of friction times distance. All right, so change in kinetic energy is final minus initial. Kinetic energy is negative. All right, so we have a free body diagram. So I have normal force is equal to the weight of the object on a flat surface. We're sliding to the right, so our friction is to the left. I know my frictional force is equal to the coefficient of friction times normal force because we're sliding on the surface. Right? As long as we slide, we can use the equal sign in this equation. But I know my normal force is just equal to my weight. So I can put this in here. Is coefficient of friction times mass times acceleration due to gravity times distance traveled. I know we stop, so we end with no kinetic energy. So I end up with negative 1/2 mass times the initial speed squared. It's all equal to negative coefficient of friction, mass times acceleration due to gravity times distance. Actually, let's instead of this, let's do something a little bit easier. Let's say from here, so I start with spring potential energy, that turns into kinetic energy, and there's no friction here. And then that all goes away. I have friction, and then I end up with no total mechanical energy. Right, that energy is taken away. So I could just call this initial kinetic energy equal to our initial spring energy. So I have 0 minus that initial spring potential energy. So let's just do that. Minus 1/2 k times distance squared. All right, so we're trying to figure out how far we go. So this is going to be, let's be distance traveled while under that force of friction. Because these distances aren't the same. This is compressed to a distance d. This travels how far we go with our friction. So these are slightly different values. Negative on both sides. So I'll see the distance traveled will be spring constant times distance squared. I have a 2 in the denominator, and I can divide coefficient of friction, mass, and acceleration due to gravity is all equal to that distance traveled on the friction surface compared to the distance compressed. So that's our expression. And then I could say if I have 1/2 of the compression, that would be k times 1/2 d squared divided by 2 coefficient of friction, mass, acceleration due to gravity. Well, 1/2 squared would be 1/4 times as much as before, k d squared over 2 mu mg. So this would be when it compressed to negative d, this is compressed to negative 1/2 d. So I see I have 1/4 the distance. So that's one way of looking at it. And then finally, D just wants us to correct the reasoning. So explain how the correct aspects of the reasoning are expressed in the mathematical relationships. So anytime they ask you to do something like that, it says you should rewrite kind of what you wrote or say as in that part. So the correct part was part A. So in part A, I said, well, less distance, so less spring potential energy. So I would say when I substituted into my spring potential energy formula, I saw I substituted in a smaller value for distance, which meant I had less energy. And then kind of write about that here. And then we can talk about uh, what aspects were corrected from part C. Well, for part B and part C, well, I corrected the idea that they said it was only going to have half as much energy, but we saw that the position was squared because I was squared. 1/2 squared is 1/4. So I ended up with 1/4 the amount of energy. So because I had 1/4 of the amount of energy, my frictional force didn't change. My force of friction is still that, just mu mg. That means I went 1/4 as far. Right. Questions on that one? All right. Well, I've been kind of working all day and like meetings constantly, so I'm pretty tired. So I think this is going to be all I do right now. Um, we will still have the class at 10 tomorrow morning. So if you have any last minute questions, I can answer them then, as long as it's not a direct question on the test, other than questions about wording. Um, no, not all teachers are required to use Meet. We're just required to meet with you. So we could just make videos and upload it, or we could just like put assignments up. Um, we're not required to use Meet though. The bigger thing is if we use a different software that's like not included in Garland ISD, then we have to like go through more things in order to make sure we're using it appropriately. So yeah, things coming up. Your NIMSY sessions, as long as you went to the first NIMSY session, you're covered. If you missed the first NIMSY session, you just have to make up 4 hours. So you can sign up for the NIMSY session. So if you need the NIMSY hours, you need to sign up for 4 of those NIMSY sessions. If you don't need the hours, you can still do those for extra credit. I'm not sure where I'm going to put the extra credit yet. I might drop some homework assignments. I might add a few points here and there on tests and quizzes. But yeah, you can go to those NIMSY sessions for extra credit, and some of them I might make mandatory depending on when we do it. But yeah, to prove you went to a NIMSY session, take screenshots, like 2 or 3 screenshots throughout, take notes over the session, and work out all the problems they work out, and you'll just upload those to. Actually, you can just email me those, I guess. The test. So the test will be posted on Google Classroom. You'll work on the test yourself, and you can either print it out and write on it, or write very neatly and organized on a piece of paper and turn it in on Google Classroom. So it'll be more like a normal homework assignment I post on Google Classroom. I will have class at 10 a.m. mostly just to work through the instructions that I think might be confusing. Yeah, if you go to all the NIMSY sessions, I'll give you a little bit of extra credit, depending on kind of what happens. I haven't decided what I'm going to make mandatory and what I'm not. So the ones right now, I haven't had a chance to look at every single session. So if you go to the ones before I even talked about making it mandatory, yeah, I'll give you some bonus points if you do those. Yeah, as long as you get 4 science hours, you're good. And I think the NIMSY sessions are going to be re-uploaded. I don't think there's anything stopping you from going to Physics C NIMSY, especially since they have, like, it sounds open. So yeah, I think you could go to it, especially the mechanics ones. You'll be surprised. A lot of the mechanics you can do without calculus on there. My cat is sleeping at the complete other end of the house. Does Great Book? I don't think the Great Book was ever closing this week, wasn't it? see. March. Yeah, the gradebook is supposed to close April 9th. So the gradebook is supposed to close April 9th. I do not know about gradebook. That's probably going to be something the district talks about sometime this week. Yeah, they probably already frozen your GPA. So if you're stressing about grades being low, it's probably not. I will say for all of probably it's probably before this cycle though. I don't know. These are guesses. I will say for grades that appear on here, if you do everything on here, then you're, or at least the majority, like, if like you don't have a perfect thinker there, if you're turning everything in, your grade is going to be good. Like I'm just going to say, if I see you around and you're turning in homeworks and assignments and taking tests, your grade is going to be at least as good as it was before. So, you cannot wait in here because if it's I don't think I think if it is frozen, they're probably not going to include anything from an incomplete 6 weeks. So if they freeze it, I'm pretty sure it'd be frozen 1st through 4th 6 weeks, not including the 5th. But I don't know. I could see getting pretty annoyed at 89. If they do try to say that they're going to lock it with only the grades we had, I'm going to be pretty upset. I will say, I think they are letting us change the grades before. So even if it did lock from right before spring break, it will be based on the grades after they've changed. So anything in the grade book from before the break is counting. But I don't know. These are all speculations. I have no idea what's happening. They're waiting to put out a more official policy on grades. But honestly, for all of you, the thing to kind of be thinking about, I'm going to make sure as long as you're working, your grades are fine. And then just be kind of thinking about the AP test, just trying to get credit for that so you have less stuff to take in college. But yeah, any other questions before I sign off? No. My day has been pretty long and busy. I feel like they're concerned that teachers aren't working, and then so they make us go to all these different meetings to kind of prove that we're working, which is obnoxious for people like me who are constantly working. And so it's like, oh, go to these meetings to prove you're working, but then I'm trying to do my normal work, and so I'm having to do my normal work and the meetings on top of it. Like I can see why they're having the meetings for a lot of teachers who are probably just, I'm just going to post a few worksheets here or there. Yeah, I mean, I definitely have higher standards than the school has for me. Like I have higher standards for myself than they have for me. So yeah. Online class, I like online class in the fact that I only have to do one class, so that's nice. But yeah, it's definitely a lot easier going over things in person and seeing you and asking questions. Yeah, I can see it being difficult to concentrate. I don't know. There's aspects of both. I'm honestly kind of a person who tries to just whatever happens, make the best out of it. It's like it really doesn't matter what I prefer. Like what happens happens. I could prefer whatever I want, and I'm just gonna end up having to do what it means. Yeah, no online equals no cat. Yeah, you couldn't see my cat. Uses Zoom and you can write on the screen. Yeah, I've considered Zoom. You just have to like download an app for it. I'd consider it. I'd consider looking at it. Oh, and then our neighbor's chicken is in our backyard. Yeah, he's normally trying to hunt the chicken. He like sits there and stares at it. Cat, where are you going? Uh, I mean, he doesn't scratch. He's really nice. I've never heard him like growl or hiss. He has like his own little couch he scratches on. Well, any last minute questions before I sign off? Yeah, he's a pretty good cat. He just gets sick all the time because we got him from the shelter. I mean, you can just get a cat from the shelter. Uh, yeah, I'm pretty sure the AP test is open now, and I don't think they can do anything but that. So, well,